We shall start a new topic. So far we have seen classical mechanics, we have seen relativity, we have seen modern physics, and we have seen quantum physics. And now the new topic that we are going to see is electrodynamics, and it's broadly categorized into electrostatics, magnetostatics, and Maxwell's equation. So we'll mostly see this electrostatics in some details, and the magnetostatics will fall almost similar, and there's a parallel that we are going to establish which will make understanding of magnetostatics to be easy. And then of course we'll do Maxwell's equations, and if time permits we'll do a little bit of wave propagation. So in electrostatics we have to deal with Coulomb's law, electric field, Gauss's law, electrostatic potential, work done in bringing a charge from some far off point, say infinity, to a point where there are other charges exist, or there is an electric potential that exists. We'll talk about Laplace's equation, and specifically we'll use a theorem called as a uniqueness theorem along with certain boundary conditions and apply the method of images to solve these potentials, basically which are solutions of the Laplace's equation. So that's the basic plan for today, but it's not very clear that how far we can do, but if we fall short of this plan, we'll continue on the next day. So let's do the Coulomb's law, which says nothing but the force between, so there are two charges, point charges, say q1 and q2, and they are separated by a distance say r, and then this law says that the force between these two charges are proportional to the product of the two charges, which are q1 and q2, and it's also inversely proportional to the distance between the two charges, or the spacing between the two charges, which goes as 1 over r square. Now, this kind of 1 over r square potential is there in many places, particularly in gravitational field. So it's the same kind of potential, so it falls off as 1 over r square. So if the distance between the two charges increases, then the force will vary, or rather decrease, as 1 over r square. If you combine these two, one can write this as F is proportional to q1 q2 divided by r square, and if I use a proportionality constant, let's say k, which is equal to k q1 q2 divided by r square, okay, where q1 and q2 are 2 point charges. So this is known to everyone, and so basically this what is this k? K is numerically equal to, if there are two charges which are of magnitude 1 coulomb each and they are separated by 1 meter of distance, then k is equal to, numerically equal to, equal to the force which is expressed in newtons. So k is actually in vacuum, it's 1 over 4 pi epsilon 0, where epsilon 0 is the permittivity of free space. We say free space or we use vacuum, they mean the same thing. Okay. And it has a value, this epsilon 0 has a value which is 8.85 into 10 to the power minus 12 Coulomb square, Newton inverse, and meter to the power minus 2. And so this in a medium, of course, it will go as this k in a medium will go as 1 by 4 pi epsilon, and this epsilon is the permittivity of the medium. So when we say a medium, we usually talk about a dielectric medium. All right. So this 1 by 4 pi epsilon 0, or this k, is often called as a Coulomb's constant, and it has a value which is 9 into 10 to the power 9 Newton meter square per Coulomb square, or Coulomb to the power minus 2. and combining these we can write down Coulomb's law, which is equal to q1 q2 divided by 4 pi epsilon 0 r square, and once again r is the distance between the two charges. But this is only part of the story because force has to be a vector. So, we have to put a vector sign, and if we do it for the left hand side, we have to do it for the right hand side as well. And if you allow me to redraw this line, so this is that distance, and the direction of the force is in the r cap direction, which means that it's connecting the two charges. So, this is the r cap direction, and this is the direction of the force, which is along the line joining the two charges. Okay. So, this is the story for the Coulomb force. Okay. And suppose there are a number of charges, 2, 3, 4, 5 charges and so on, and you want to calculate the force between them. So, it will act or rather it will add up vectorially that they will all have so there will be a superposition of these forces between various charges. So, the net charge will be a vectorial form or a decomposed in the coordinate system that is convenient to you. So, you will have a f x, f y and f z for all those charges which are interacting, or rather which are feeling a force with each other. Okay. So, let us call this as the electromagnetic force, or it is really the electrostatic force, but so let us call it electrostatic then, because these two charges are at rest. So, this electrostatic force, or it is also called as the electromagnetic force, because when the magnetic field is coming into picture. And if you categorize the four forces that we have in nature, which are called as the strong interaction, then we have electromagnetic interaction, I mean interaction, what we mean is that we are talking in terms of potential, but they would mean the same thing, that there is also a force associated with these particles which are interacting either strongly, or they are interacting via electromagnetic interaction and so on and so forth. So, and then we have weak interactions. We have written interaction, but you can simply change this word interaction by forces, they will not make any difference here. And gravitational interaction. And to tell you, if this we scale it to 1, that is the highest force or the strongest force. If this is 1, then electromagnetic forces are of the order of 10 to the power minus 2. The weak interaction is 10 to the power minus 10, and the gravitational interactions are usually of the order of 10 to the power minus 38. Okay. So, how strong like the electromagnetic interactions and the gravitational interactions, if we take a ratio of them and try to calculate this ratio, that is F gravity divided by F, let us call the electromagnetic, by EM, and do it for an electron. So, we have electronic charge equal to 1.6 10 to the power minus 19 Coulomb, mass to be equal to 9.1 10 to the power minus 31 kg, and we have given this 1 over 4 pi epsilon 0 in the last slide. So, the gravitational interaction or rather the gravitational force has a scale which is 6.6 into 10 to the power minus 11 Newton meter square per kg square. And so, the gravitational interaction will have this form, which is G m1 m2 divided by r square, along with again the, if you write it in the vector form, there will be a r cap direction which is connecting the two masses. So, these are the two masses that we are talking about, and now both the masses can be electrons. So, we are trying to calculate what is the gravitational force between two electrons. And with respect to the electromagnetic force, where it will be like the E square and then all these other things k into E square by R square. And if you keep them at the same distance, because the distance will cancel out if you take the ratio, and this really comes out as 10 to the power minus 46. So, you understand gravity is 10 to the power minus 46 times smaller, which is an enormously small number compared to the electromagnetic force. So, electromagnetic force is quite strong, at least as compared to the gravitational force. And as you see in this ordering of the forces, it is only 2 orders of magnitude lower than the strong interaction. Okay. So, now introduce quantity which is quite important in the context, that is called as an electric field. And this even though the force is not a measurable quantity, it can be measured by indirect means by taking a force balance equation with in an appropriate way. But what the electric field is a more sort of physical quantity that's or relatable to real situations. So, we define this electric field as the force. So, electric field E is equal to the force experienced by a unit positive charge. Which means that it is basically, suppose so this is a force, or rather if you have a force, then this is a force divided by the charge. We made it equal to 1 such that E becomes equal to F, but it is basically divided by the charge. So, that is the electric field due to a charge. So, we can just like what we have done for the force, that is it's Q1 Q2 divided by 4 pi epsilon 0 r square, we can calculate the electric field just by dividing it by one of the forces. So, if you are still talking about Q1 and Q2, you could ask the question, what is the field, electric field due to Q1 at a distance r, which means where the charge Q2 is located, and that is given by, that is equal to the force divided by this Q1, and that will give you the electric field that exists at a distance r where Q2 is located. So, that is the electric field that Q2 is going to feel due to Q1 being present at a distance r. Okay. So, that is what is shown. I have chosen a different charge with a capital Q for a general definition, but this is how the electric field is defined. Okay. So, there is I mean we are so far talking about electric field for discrete charges and Coulomb force for discrete charges. So, this will of course tell us that this discrete case we still have a 4 pi epsilon 0 r square, and if you write it in a vector notation, it is still r cap. Let us see what happens for continuous charge distributions. So, you do not always have discrete charges that you find in nature. Discrete charges, finding a point charge existing in nature is not possible. So, we usually talk about continuous charge distributions, and the expressions for these continuous charge distributions is the following, that you have for a line charge, or let us write down a sort of general formula for this electric field for a continuous charge distribution at a given point r, which is at a distance from this charge distribution. So, what I am trying to say is that suppose you have a linear charge distribution. So, there is a wire which has charges pasted on it, and you want to know what is the electric field due to this charge distribution. This is exactly one of the problems that we are going to do. And the general formula for this for that distribution is that we have these r cap divided by r square, and dq, where dq is a small element of charge. And what does this vector mean? We have written a sort of unit vector as well as this vector's square, or rather the magnitude of the vector square in the denominator. So, this is equal to r minus r prime. Now, this is very important for you to remember, because this is really the source point, and this is the field point. What do they mean? They mean that the source of charge is located at r prime with respect to some coordinate system. Suppose you have a coordinate system here. So, that is the origin of the coordinate system, and you are talking about a dq charge here. So, this is your r prime, okay? And you want to calculate this electric field at this point P, which is at a distance r from the same origin, okay? So, this distance, which is the the distance between these 2 points, or the resultant of this. So, one is r prime and this is r. So, this would be r, this curly r, which is equal to r minus r prime. Okay. So, that is the definition of this curly r, and the unit vector associated with this curly r is that r cap vector. So, E r is equal to 1 by 4 pi epsilon 0 r cap by r square. And if we now do it, this I have given you a line charge example. We can have a charge which is on a surface. Okay. So, there is a surface charge. So, everywhere there is a surface charge density. So, usually a line charge density is denoted by lambda, which is equal to the total charge divided by the length of the the wire, or length of whichever element that the total length of the element where the charge is distributed. And this is the surface charge, and which is denoted by sigma. Sigma is basically the total charge divided by the total area of this. So, it's called a surface charge density. Or you have a volume, okay, it is a closed volume where you have a volume charge density. This is not a it is a sort of solid area where we have a volume charge density. So, you have charges everywhere. So, lambda we define as a linear charge density. Then we talk about sigma to be surface charge density, and then we talk about rho, which is the volume charge density. And if you use these three, that is, if you want to calculate for a linear charge or a surface charge or a volume charge, the electric fields at this point r is the field point where you want to calculate the field. So, that is called a field point, r prime is the source point. So, this is equal to so 1 over 4 pi epsilon 0, which will come out, and you have a lambda and a dl prime, that is a primed variable because it is inside the integral. So, you will integrate over all L, and so this is equal to this r square, and it has a direction which is the r cap direction, and that is it. So, lambda dl prime divided by r square into r cap. It is not clear that whether lambda is actually a function of is a constant or a function of maybe r prime, which means that it varies from point to point. So, you can write down lambda with this dependency on this at every source point. It may be varying in some fashion, but nevertheless this is the form for this electric field due to a linear charge distribution. What is it for the surface charge distribution? The left hand side of course remains the same, with 1 by 4 pi epsilon 0 remaining same as well. This is that sigma, once again we assume that there is a variation there, and then there is a ds prime divided by r square, and this is interestingly this would be r cap vector, but this r cap vector in this case, so the r cap vector is still with respect to just the way we have shown. Let me just show it once for this thing. So, this is the surface charge density with a charge sigma, and this is the point where you want to calculate the electric field. And suppose you have a coordinate system, some arbitrary coordinate system whose origin is here. Now, you take a small surface area here which is ds, because it is inside an integral we take a ds prime. So, this is your r prime vector, this is your r vector, and this difference between the two is your this vector, and the direction is in this direction. Okay. So, that, and similarly for the volume charge, it is equal to 1 over 4 pi epsilon 0, and we have a rho r prime again and a dv prime r square r cap. Okay. That is the definition for all these different charge distributions. Okay. So, one can do a lot of examples in this. Let me do one example which is quite well known and is done on all books. So, we take an infinite sheet of charge. Okay. So, it is a sheet of charge, which means that it has surface charge density, and we say that with uniform sigma, okay, which means that uniform surface charge density. So, this is the, it is in the plane, and we want to calculate it at this point, and let us just draw this coordinate system like this and like this and so on, and then take some small element. Let me show it by some patch here. So, we have taken this to be the elemental, so that is the ds containing some charge, and so let us just show this by this is, so that is your this point is, let us say P, and this is theta, and this is your from the origin of the coordinate system, this is your r prime, and you want to calculate it here. So, this is the point that you want to calculate, and let us call it, so you have this as a y axis and this is x axis. So, this point has some coordinate which is given by x and y, and this is your z axis, okay, and this angle says phi and contain uniform charge density sigma, and this is your that r where you want to calculate this point. Okay. So, this vector that you see, let me show the vector. So, this vector is this r, and this vector is that the normal r. Let me write that. So, this vector is r, and that vector is r prime, this vector is r prime. If it is not clear, because we have so this is r prime and so on. Okay. So, this is a picture, and this is a schematic diagram of an infinite sheet. So, this looks finite, but it is actually infinite. So, you can sort of make that distinction, and we want to calculate what is the electric field at this point due to this infinite charge distribution. So, this has cylindrical symmetry. Okay. The whole problem has cylindrical symmetry, because you have some, say, the board of this the screen that you are seeing on the board is the plane in which has a uniform charge density, and you are talking about a point which is vertically on top of this the surface. Okay. So, the coordinate of the field point which is P is 0 0 z. Okay. So, it is purely on the z axis, okay, and you want to calculate it on the z axis. Okay. So, E would be purely along the z axis, and this would be equal to this over the entire surface, which is S, it's like the sigma dx dy and a 4 pi epsilon 0, which can stay outside if you wish, and there is a r square. And now because it's in the z axis, so this angle is phi. So the z direction, this will be along the cos phi, because for this element it will be in this direction, okay, I mean along that line. Draw it a little better, it's along this line, okay. So you take the projection along the z axis, so that's why the cos phi comes, phi angle is shown, sigma is the total uniform charge density, and dx dy is that small area which is painted in red, and this we want to calculate the electric field at the point P due to the small element of charge that is there. So, if you look at the figure, cos phi is nothing but equal to z over r, this r, okay. So, that is the angle, because this angle is making a right angle at the origin, and we also have r square, this is equal to x square plus y square plus z square. That is when it is resolved in the 3 coordinate systems, and this x square plus y square is actually equal to rho square in the cylindrical coordinate system. So, we write it in terms of rho phi z. So, it is rho square plus z square, okay. So, your cos phi is again z over r. So, E z, which is equal to these expression that we have written, now we have to do an integration over. So, minus infinity to plus infinity and minus infinity to plus infinity. We have sigma dx dy and then z, okay, we can write this z here, and then we have a 1 over 4 pi epsilon 0, and now we have these x square plus y square plus z square whole to the power 3 by 2. There is a bit of a problem in doing this integral, because it will look like that it is not a very convenient integral to do, because these limits are minus infinity to plus infinity, and you have a dx dy in the numerator with these x square, y square and z square. But if you transform it into the polar coordinate system, it becomes easy, because your dx dy becomes equal to a rho d rho d theta, right. And because if you do this integral, it will give you this pi r square, okay. So, rho d rho will give you a rho square by 2, and theta is from, or this is like phi actually. So, this is rho d rho, and we do not have, I mean we have of course written down a theta, but this is actually theta, because that is on the plane, rho d theta. We have shown d theta here. D theta is the angle that you see which these small element makes with the x axis, okay. So, it is rho d theta. So, Ez becomes equal to 0 to 2 pi and 0 to infinity, and sigma rho d theta, and then you have a z there, and then you have a rho square plus z square whole to the power 3 by 2. And if you take this rho square plus z square equal to some other variable, say that is equal to this xi square, then this becomes equal to a pi sigma z, and we have a 4 pi epsilon 0 that I have forgotten here. So, it is 4 pi epsilon 0, and we have this integral from zeta equal to z square to infinity, and this is this zeta to the power minus 3 by 2 d zeta, and this is equal to a constant which is sigma over 2 epsilon 0. So, this is an interesting result, and why it is interesting is that if it is an infinite sheet, whether you take it at a distance h or at a distance 2h, or anywhere you take this point where you want to calculate the field, it's always a constant and has a value which is sigma divided by 2 epsilon 0. And so this is the one that is makes a lot of things easy, and will again derive the same result when we get into Gauss's law. Okay. So now let us go to Gauss's law and sort of look at various things that are important. So what is Gauss's law? Okay. So Gauss's law gives you so it gives you a handle to calculate electric field, and it says that the closed surface integral of this quantity is equal to the q enclosed, whatever q is enclosed, divided by epsilon 0. So this is called as a flux of the electric field. E is the electric field, E dot ds is the flux. So whenever you multiply or rather take a dot product of the vector with a surface, and surface has a direction which is unit drawn normal. So suppose we talk about a sphere and want to calculate the n cap. So the n cap is in this direction, which is so there is an element of surface say ds, and the direction is in the unit drawn normal. For a sphere, this becomes same as r cap, which is a radial vector that connects this. But say you take a flat sheet and you want to calculate what is ds, that is the outward drawn normal. So ds is the vector which is along this n cap direction, which is the unit drawn normal. So this normal direction, so it's a flux of the electric field, and the direction of that the surface area is the unit drawn normal, and E is also a vector which has a direction. Somehow if this two directions are orthogonal, then of course that there is no flux of the field in that direction, but at least in this problem with spherical symmetry, the r and the n cap are in the same direction, and they'll sort of just the dot product will just behave like a scalar quantity. In any case, whatever the charge is enclosed in this region, maybe there is a charge at the origin, or there may be a charge here with a q1 and with q2 and with q3. So the law says that the flux of the electric field is equal to the total charge enclosed, which in this case is equal to q plus q1 plus q2 plus q3 and all that, okay, divided by epsilon 0. If one of them is negative, say it is a minus q2, we will have a minus q2 here. Okay. So that is the net charge or the enclosed charge through this, or the flux of the electric field through this area is equal to the charge enclosed divided by the epsilon 0. Okay. So now there is one relation about the divergence of the electric field that will emerge if you take this equation, the left hand side of this equation, or the Gauss's law, and use Gauss's divergence theorem. And what is divergence theorem? Divergence theorem says that this elementary vector calculus, you can look it up. It says that for any arbitrary vector, okay, which is a sort of a good vector, which means that it has all the properties of a vector and so on, this is equal to a divergence of A and a dV. Okay. So this is like a closed surface integral, and this volume actually defines the surface. So basically, if you are talking about a sort of cylinder, okay. So the surface in this case are the surface which is a curved surface. Let us call that as S1, the curved one. And this is the flat surface ds2 or S2, and this is another surface which is S3, which is below, and in each of the directions we have shown the arrow actually shows the vector. Okay. So, these are the surface and the volume is this entire cylinder that you have. Okay. So, this is that volume and the surface area are these three surface areas that you see. For a sphere it is very easy because that is the surface area and the volume is basically what the sphere encloses. So, the surface actually is the covering area of the volume that you are talking about. Now, if this is true, so you need to take a divergence, and I will not go too much into this divergence, gradient and curl, but just to tell you in one line, gradient, let us start with the gradient. Gradient is actually the direction in which a function changes the fastest. So, if you talk about a hill, so at the topmost point you can actually calculate the gradient to know which direction it is changing the fastest. Divergence is how a vector diverges, whether it has any divergence or it does not diverge at all. So, that is given by the divergence. So, if you take a divergence of a vector, arbitrary vector r, which is monotonically going away from the origin, it is x I cap plus y j cap plus z k cap. This is equal to 3 because it diverges equally in all the x, y, z directions. So, it is how, just like this, for a point charge, if you draw the field lines, that just looks like this. So, that is the divergence of the field. So, that is how electric field behaves in the vicinity of a point charge, and that is exactly what R vector also looks like, and we have showed that. I mean, we have shown that this direction of the electric field is the r cap direction, which is in the radial direction. And the last thing, that is curl. Curl is the is a measure if the vector circulates in space. Okay, if it does not circulate at all, then the curl of it is 0. And this curl of a vector being 0 has other consequences, and it is said that if the curl vanishes, then the vector field is conservative. Okay. So, the closed line integral of that vector field, which means the work done due to that vector field over a closed path, is equal to 0. So, these word conservative, when curl of a vector field equal to 0, say curl of A equal to 0 means the vector field is conservative, and it also means that the closed line integral of the vector is also 0, which means it does not do any work if it goes in a closed path and comes back to the same point. So, definitely R vector sort of diverges in space and it does not curl around. And if you want to sort of in a real life, if you want to understand where this curl arises, if you open a tap and look at the water passing out through the the nozzle, you will see that the water field or the vector associated with the water flow that circulates as it goes down through the through the nozzle and so on to the outlet. So, a curl of R definitely is equal to 0. So, as soon as you see a vector field which has a direction which is like r cap or in a given direction in space, then that vector has a curl to be equal to 0. So, by that argument it is easy to see that all these forces or all these fields that we are talking about, the field associated with the gravitational interaction or the field associated with the electromagnetic interaction, with both of these are they have a direction which is connecting the two charges or connecting the two masses. The curl of that field is 0. So, curl of these electrostatic fields or other fields which has a dependence, or rather which has a direction which is r cap, that is equal to 0. So, this tells us that if we apply this theorem, coming back to this Gauss's law, if we apply this Gauss's divergence theorem, then we get that the left hand side becomes equal to divergence of E dV, it is over a volume. So, there is a volume here, and this is equal to Q enclosed over epsilon 0, and if we are allowed to write this q enclosed to be equal to some rho dV for a continuous charge distribution. Now you see that divergence of E minus a rho of epsilon 0 and over some arbitrary volume equal to 0. So, dV equal to 0. Now, that tells us that if this integral is equal to 0 for any arbitrary elemental volume, then the integrand has to vanish. Okay. So, that tells us that divergence of E is equal to rho by epsilon 0, and this is another form of Gauss's law. Okay. The integral form is given by the first line of this slide, and the differential form is given by the divergence of E, which is del dot E equal to rho over epsilon 0. So, this is in SI unit. If you read an old book which is written in CGS units, you will see instead of a 1 over epsilon 0, you see a 4 pi. So, it is a 4 pi rho. Okay. So, let us just whatever we have seen, let us see that once more, and that is that infinite sheet of charge. And so, once again that infinite sheet of charge, I will just now draw it like this, but it is the same thing, it is just infinite sheet of charge containing charge sigma. Now, what we do is that let me write that sigma somewhere, and we want to apply Gauss's theorem. So, there is an example. So, what we do is that we construct a pillbox, the boxes which one uses for keeping the medicine, that is called as a pillbox, and this is slightly going above, and by it is slightly going below. Okay. And this is what the interface is. Okay. So, it is slightly jutting out of the plane on the upper side, and it is also jutting out a little on the lower side. So, this is like that small thing, and the plane goes through in between. Okay. So, we have this for this surface, this is the this is the n cap, and for this other surface, this is the direction of this n cap. Okay. And the electric field will be like this here in this direction, and the electric field will be like this in this direction. Okay. So, this is called as a pillbox, and this will act as a Gaussian surface for us to apply Gauss's law, which we have learned for electrostatics. So, this is the Gaussian surface, and the whole point about this surface is that it is a closed surface such that we can apply this Gauss's law, and that because it is a uniform charge density. So, that the surface of that thing here it contains that sigma, the charge density. So, the charge that is enclosed contains that same charge density that is there. So, it's E dot ds, this is equal to q enclosed over epsilon 0, which is sigma into A, where A is just the area of the pillbox, the top area of the pillbox. And indeed, the pillbox is actually cylindrical in shape. So, it has also a curved surface, but the curved surface is actually along the plane, and because it is along the plane and the electric field is in the perpendicular direction, which is out of the plane, the curved surface does not give any contribution to this flux. Okay. So, this flux gets no contribution from the curved surface, and it is only the top surface which is little jutting out from the plane, and the bottom one which is slightly coming down from the plane, they contribute, and we have so this is sigma A by epsilon 0. So, we now are convinced that for this pillbox the curved surface do not contribute, and the two top and the bottom they contribute, and so this gives us it's equal to this E dot ds is really equal to twice A of E this is equal to sigma A by epsilon 0. So, we do not need to write this, maybe we can just simply write it as A, because we know that A and ds are along the same direction. So, the dot product will be same, I mean just as like a scalar. So, E is equal to sigma by 2 epsilon 0, the result that we got, and if you want to write it in the vector form, it is sigma by 2 epsilon 0 n cap is a result that we just saw. It is a sigma by 2 epsilon 0. We have not put the direction here, but the direction is perpendicular to that. So, instead of doing this integral by this all this change of variables and trying to do an integral, the problem is much simpler here, where you simply apply this divergence theorem and got the result. Okay. So, let me take another note of this divergence of E, and so okay. So, E is equal to 1 by 4 pi epsilon 0, and we have this r cap by r square rho r prime dv prime, and just once again to make this notation clear, it is r minus r prime, and this r cap is equal to r minus r prime divided by r minus r prime. Okay. So, that is the unit vector. Okay. So, divergence of E is simply the divergence of this quantity, and so its divergence of r cap by r square and rho of r prime dv prime. Now, interestingly, this divergence only acts on the r variable. So, which means that it only acts on the field variable, not on the space variable. And so, we need to only consider this divergence and do not need to worry about divergence of rho, which may still exist. Okay. But we do not need to talk about that. So, we have this term which is divergence of r cap by r square. Now, this without a proof, I will say that this is the definition of the delta function. Okay. So, the delta function means that, so delta of r is equal to infinity at r equal to 0. I mean, so at r equal to 0 means x, y, z or r theta phi, whatever you say, it is 0. But the good thing is that it is an integrable function, which means that delta r d cube r, this is equal to 1. Okay. And not only that, if you take any other function and consider this r minus a, I am writing it in terms of scalar notation, and let us just write it as a one dimensional thing. So, this is equal to, or rather this is f of r, not f of a. So, this is equal to f of a minus infinity to plus infinity minus infinity to plus infinity. So, even if the function diverges, the integral remains finite. So, that is a property of this delta function, and divergence of r, this unit vector r curly r by this curly r square is equal to a 4 pi delta function. Okay. So, the divergence of E now then comes out as divergence of E, if you put it, so 1 over 4 pi epsilon 0, we have this 4 pi which we can bring it there, and we have a delta of r, and we have rho of r prime dv prime, using this property that f of r delta of r minus a equal to f of a. So, this is equal to rho of r. Okay. And this 4 pi will cancel. So, this is equal to rho of r divided by epsilon 0, and this is what we said also can be obtained from the this Gauss's divergence theorem. So much for the electric field and the Gauss's divergence theorem. Now, we will talk about the electrostatic potential in very brief. Okay. And what we mean by electrostatic potential is that it's basically the potential due to a single charge or charge distribution that we have. And for any of this force we have or any of these fields or even the force, we know that the curl of E is equal to 0 because its E is in the r cap direction. Okay. So, if this is 0, then we can write this E to be equal to a minus gradient of a scalar function. So, the electric field can always be written as a minus gradient of a scalar function if the first line is valid, which means that if curl of a vector field is 0, then that vector field can always be written as a negative gradient of a scalar potential. And this tells us that this negative, this scalar potential here is the electrostatic potential. And just like these electric field, the electric potential has a form which is 1 by 4 pi epsilon 0. We have these rho of r prime, and there is a root r, and then there is a dv prime. So, do not confuse between v which is a potential, and the dv that we talk about here is the the volume element that we sort of say. Okay. So, I think it is clear because the gradient of a scalar quantity or a function, it gives you the direction in which the function changes the fastest, right. So, that is a given direction, and the curl of that direction equal to 0. So, these two equations are consistent, because if you put E equal to grad V, then curl of a gradient should always vanish. Okay. So, that is why you can write this, and this it has this, for a charge distribution it has this form. Okay. So, what does this physically mean? So, suppose you have a charge, say you have a test charge Q, which you transfer from point say P. We cannot say P and Q because it is already Q. So, transfer from a point M to a point N. Okay. So, the work done in moving this charge, or there has to be some work done by the potential or by the field. So, this work done is nothing but equal to this is a minus F dot dl, and from this point M, initial point M to a final point N, and this is equal to a minus Q, and from this point M to this point N, and this is Q E dot dl, E dot dl. Okay. dl is the path along which it is moved, and E is equal to minus grad V. So, the minus sign goes away, and we have M to N and a grad V dot dl, and that gives you that this is equal to a Q into V N minus V M, that is difference in potential between the 2 points. Okay. So, this is the physical meaning of this electrostatic potential, which is nothing but the change in the potential energy or difference in potential energy between 2 points. And how do we understand these 2 points? You can take a test charge and move this test charge between the 2 points from one point to another. The work done will be stored as the electrostatic potential energy, and you divide it by the charge concerned, the test charge that you are talking about, that will give you the electrostatic potential. Okay. So, that is not difficult, and you have the general form of this this charge distribution for a given charge distribution. Let us see that what the electrostatic potential takes a form. So, this potential energy or the work done, they are same. So, this is equal to half rho into V. V is the potential, and this is a dV. So, this is a volume. So, I actually, let me make this this V, let me make it a little curly V with a small thing, so that capital V, which is potential, and small v, these are sufficiently different. Okay. And this is also equal to half of this sigma V ds, and so on and so forth. Okay. All right. So, that is the work done, and what you can do is that you can use this rho to be, I mean, this is not required, we are just talking about the volume charge. So, rho is equal to epsilon 0 divergence of E, and if you put this W equal to which is the potential energy or the work done, this is equal to so there will be a epsilon 0 here, and there will be a divergence of E into in V, divergence of E, V and dV. And if you need to this integrate this, then you do integration by parts. So, by parts, if you do integrate, then this becomes equal to, so this W is equal to epsilon 0 by 2 and this E dot del V dV plus there is another term which is V E dot ds, that is the surface term, and so on. So, this is there. This is a general definition of that, but then this term, the surface term, actually does not contribute, because this goes as 1 over r, and this goes as 1 over r square, and this grows as r square. So, the whole dependence is still as 1 over r. Now, this term can go to 0 if r goes to infinity. Okay, which means that even if this work done expression or the electrostatic potential energy expression involves a volume integral and a surface integral, we can make the surface integral go to 0 by taking that surface to be at infinite distances, and we are left with only this volume integral, and this is nothing but epsilon 0 by 2 E squared dV. Okay. So, this E squared dV is the expression for the electrostatic potential energy. All right. So, let us, so we have now learnt about force, we have learnt about electric field, we have learned about Gauss's law and how that gives the flux of the electric field. We have now learned the electrostatic potential, which is nothing but the work done, and finally, at least till whatever point we can do it today, we will show that the Laplace's equation, which gives you a solution for the potential. Okay, so, we have this divergence of E, that is equal to rho over epsilon 0. We have also learned that curl of E is equal to 0. If you combine them, then E becomes equal to minus gradient of V, where V is the potential. So, if you put divergence of minus gradient of V, this is equal to rho by epsilon 0. This gives that this del square V, this is equal to minus rho by epsilon 0. This is an equation called as the Poisson's equation. Okay. And this operator is called as a Laplacian, and that is why it is called as a Laplace's equation. Okay. So, this del square V equal to minus rho by epsilon 0 is a second order differential equation for V, and this has to be solved for either a given charge density, and it could also be true that there is no charge density in space. So, which means that there is no charge density that exists, in which case it will give you this Laplacian of V is equal to 0, and this is really called as a Laplace's equation. And just like the Poisson's equation, you have a right hand side which is non-zero. Here you have a right hand side which is equal to 0. Okay. And now whenever there is a differential equation that you need to solve, you need to have the boundary conditions. And so we need boundary conditions, and because there's a second order differential equation, we need two boundary conditions. To solve for V. And what are the two boundary conditions? One boundary condition is that, remember, the electric field is a vector. So, electric field has got components. So, we are not talking about two media separated by an interface. So, there is a sort of one media and there is another media. So, there is a medium 1 and there is a medium 2. And this is actually not a line but a surface. So, it is like just separating two media in 3 dimension, and so the surface, the interface is actually a surface which is 2 dimensional. So, we have this the two boundary conditions that we have are electric field. So, it is a perpendicular component. So, one component of the electric field would be along the plane, which we will call as a parallel component, and we will have a component which is so that is a parallel component, and we also have a component which is perpendicular to the field to the plane, and this is called as a E perp, or written as E this one. So, that is the perpendicular component, and we have this parallel component. So, what are the boundary conditions? And the boundary conditions say that E above minus E below, that is for the perpendicular component, this is equal to sigma over epsilon 0, and it is coming from this curl of E equal to 0 and divergence of E equal to. So, this coming from really the divergence of E is equal to rho by epsilon 0. So, that is the the form for this, and divergence is the perpendicular component, because when you take a divergence you so this is like a dot product. So, we are really talking about the perpendicular component perpendicular to the plane. If of course sigma is 0, there is no charge density on the surface, then of course this is continuous, which means that it will be E above mine equal to E below. Okay. And similarly, we have so the V above is always equal to V below. It does not matter whether we have this charge at the interface or not. And so, del V above minus del n is a unit drawn normal, which is nothing but the field. This is equal to del n, which is sigma by epsilon 0 n cap, which is the same as equation 1. So, this is equation 2 and this is same as equation 1, just stated in this form of so this is really that n cap direction. So, either 1 or 3, let us call this as 3 and 2. So, 1 and 2 or 3 and 2, these are the boundary conditions that we have. And this is basically for the electric field in the parallel direction. So, E parallel above is equal to E parallel below, and this is simply coming from the curl of E equal to 0. And if that is not satisfactory, then you can write it as E dot dl equal to 0 as well, because curl E ds equal to 0, and applying Stokes theorem we have E dot dl equal to 0. So, let me just briefly state Stokes theorem. So, it says that for any vector field, the line integral of the vector field is the curl of the surface integral, okay. And the relation between the surface and the line integral is that. So, there is a surface, and so there is S, and this is that L or dl, okay. So, this is 1 and this is 1 and this is 1, and we get 3 because electric field is a vector. Okay. It is important to note that I mean, you have a relation E equal to minus grad V. V is this potential, and it can be questioned that how a scalar quantity, potential is a scalar quantity, how a scalar quantity can give information about the vector quantity. And the reason that it can give is that because the curl of E is equal to 0, which means that all these relations, or rather there are additional relations between the x, y and z components of the electric field coming from the curl equation. So, it is not only E equal to minus grad V, it is also curl equal to 0. That enables us to get a complete description from a single scalar function, this information about E. Okay, so let me sort of get into this solution of the Laplace's equation by method of images. And this is really a trick. And why it is a trick? Because it uses one very important concept, that if you somehow can find out for this solution of this V equal to 0 or equal to rho by epsilon 0, if you can find out a solution for V which satisfies all the boundary conditions, then that is the only function and there is no other function. Okay. So, you have found the solution. Is somehow if you can find out these V which satisfies the boundary condition, then that is it. I mean, there is no nothing required, and this is called as a uniqueness theorem. So, that uniqueness theorem guarantees that this trick that you may have applied is the right trick. Okay. So, it comes from the uniqueness theorem, and let us take a a sort of a point. So, there is a conducting plane. That is the first part one does. So, there is a conducting plane, and then there is a point charge, and you want to find the potential everywhere, and let us say the conducting plane is infinite, so that you do not see what is there below. So, the Q is at some distance d or d or a above this plane. Okay. So, let us so this is at a distance a there. So, you want to find everywhere here, okay, all these places that you have, you want to find the potential everywhere. Now, it could be, you could say that it is Q by 4 pi epsilon 0 r square, which is what we have, or 4 pi epsilon 0 r, because this thing has, let me go and check whether, yeah, this is r. So, its potential is 1 over r, and electric field is 1 over r square. But that is not going to work, because this charge is going to induce charges, negative charges on the surface, assuming that Q is positive, and there will be also potential due to this induced charges, but there is no clear cut method how to calculate these charges or this induced charges. So, what you do is that you completely change this problem to a problem where you do not have anything, you do not have a conducting plane, but you have a charge at a distance a, and you also have a charge at a distance minus a, I mean this is, you have a charge which is minus q again at a distance a, but in the other direction. So, it is a minus q. So, this is imaginary, that is, there is no line. It just simply is a reference point, because this is where the earlier this thing was situated, the conducting plane was situated. Okay. And what are the boundary conditions that we have? We have V equal to 0 at Z equal to 0. So, we will sort of set our, so this is Z equal to 0, and we have these. So, z equal to 0 is the plane, say for example, and we have this q having x, y, z, etc., and minus q have some x, y, z in the other direction, and the plane is located at z equal to 0 and v equal to 0. Why? Because it is a conducting plane. Okay. And also there is one boundary condition. We do not need the electric field boundary condition here, but we have, so v equal to 0 far away from the plane, which means that far away means x square plus y square plus z square is much greater than a square. Okay, so that is the two conditions that we have. And if you can write down a potential function which satisfy both these conditions, then that would be the solution. And let us write down these things as v x y z, which is 1 by 4 pi epsilon 0, and we have this q divided by root over x square plus y square plus z minus a whole square, and this is for the top charge. And then there is I do not know what these q is, but we can you can write down a q prime and root over x square plus y square plus z plus a whole square, and this if you put the boundary condition, that is v at x y z equal to 0 for z equal to 0 and it is equal to infinity, it is equal to infinity for x square plus y square plus z square greater than a square, that basically the two boundary conditions that you just saw, then you will see that your q prime is equal to minus q. Okay. So, we get q prime is equal to minus q, and that is why it is called as an image charge. If you look at q and minus q, we did not know initially that it was minus q, but suppose we have a q prime when we wrote it as q prime and apply the boundary conditions, and you will have a q prime equal to minus q. Okay. So, now if you want to understand that what is the charge density that is induced on the surface, that is minus del v del n, and this n is nothing but z here. Okay. And where is it induced? It is induced at z equal to 0. So, we will change this n to be equal to z, and if you do a del v del z, you get 1 over 4 pi epsilon 0, and we have these minus q z minus a and x square plus y square plus z minus a whole square whole to the power 3 by 2 and plus q z plus a, and so x square plus y square plus z plus a whole square. So, this so z plus a whole square, and we have a 3 by 2, and now if you put del v del z and calculate at z equal to 0, you will get it at so this is sigma, which is a function of x y, which is minus q a divided by 2 pi x square plus y square plus z square and 3 by 2 and so on. Okay. So, this is a negative charge. So, the induced charge is negative because of the negative sign and so on. And if you want to calculate, so if you want to do a sigma ds, that is the total induced charges, you will still get all these things. If you put and transform it into exactly the same way that we have done it for these cylindrical coordinate system, you will get it as minus q. So, the upshot of this problem is that this potential that you have written down purely by changing the problem from a q in front of a point q in front of a plane, conducting plane, to by removing the plane completely and putting two charges, say q and q prime, later on q prime came out to be minus q, and wrote down these potential functions purely from this by this trick, applying this trick. It satisfies the boundary conditions that you need, that is because it is a conducting plane, you have V equal to 0 and on the plane itself, and V at very far away should also be 0 because there will be no effect of the potential at very far region. So, that is the only solution that one has. Okay. As a last problem, you can do it for a sphere, and so this sphere is also simple. I will just show you the so there is a sphere, conducting sphere, say of radius r, and you have a charge which is again put at a distance maybe a from the center of the sphere, and now again it is a sort of say earth sphere where potential is equal to 0 and this 0 here. So, what you do is that you replace this problem and only write this the sphere, and there is this charge here which is the original charge, and then there is a charge which is somewhere inside, which let us call it as a q prime, and these distances are important, and we want to calculate the potential at any arbitrary point, and these arbitrary points are these things. Okay. So, we have these let us call this distance as b and this distance as r, and this angle is theta, this is r prime, this is r, and I removed the sphere completely. The sphere was drawn as a reference for me to know where this q prime is located. See, the q prime cannot be located outside the sphere because that would alter the potential. So, the q prime will actually be inside the sphere. Now, there is no sphere, but we have to understand this, or rather visualize this sphere to be still there, so that q prime is inside, and this distance is of course a. And if you again write down V of q, V at some r, which is 1 by 4 pi epsilon 0, and this is like q over r plus a q prime over r prime, and then this in this spherical polar coordinate system, this is 1 by 4 pi epsilon 0 q divided by root over of r square plus a square minus 2 a r cosine theta, and so this is and then there is a q prime which is equal to r square plus b square. The distance b is shown, that is a small distance, minus 2 b r cosine theta, and then we have this. Okay. So, that is the potential, and we have to see that whether this potential satisfies the boundary condition, and we have two unknowns, q prime and b are unknowns. And how we can calculate this? We take two useful points, and we can take any theta, that is any theta that is on the surface of the sphere, but we take two thetas which are useful, and these thetas which are useful are theta equal to 0 and theta equal to pi, in which the cosine takes values which are simple, either it is 1 or minus 1. So, if you take these two values, then q divided by a minus r plus q prime divided by r minus b, this is equal to 0. So, this for theta equal to 0, and we also have q divided by a plus r plus q prime divided by r minus b, this is equal to 0 as well. So, this is for theta equal to pi. Now, you see this equation 1, this satisfies the boundary condition, because at small r equal to capital R, it will go to 0, and of course, at very large points or very far off points, it is still equal to 0. So, if you solve these two equations, what you get is that you get a q prime equal to minus r over a into q, and b equal to r square over a. Okay. So, both our assumptions are satisfied, q prime has a negative sign, which means the image charge which is inside the sphere, that imaginary sphere, is negative, or rather it has an opposite sign, with respect to q, and where it is located, which is inside the sphere, that distance b is actually less than r. Okay, so because a is greater than r, and this is how the entire problem has been changed from the solving of the Laplace's equation. We did not have to do it directly, but what we did was apply a trick and write down a potential function that satisfies all the boundary condition. And this is a very nice sort of trick that works because of the uniqueness theorem, which says that is the only potential. If you have found one, that is the only potential. So, we will stop here and we will continue next day. Thank you.